Refactoring is another aspect of high-level software architecture. Refactoring is the process of updating your design as you go along. So we all want to work in these nice, tight, iterative cycles now. Our design is no longer an initial step of a project before implementation. We go in a tight cycle and we're constantly redesigning and re-implementing as we learn more about what we're actually doing from the experiments that we're performing. So refactoring was popularized by Martin Fowler in his excellent book, Refactoring. It's subtitled Improving the Design of Existing Code, which is a nice definition of what refactoring is. So this is not just code level redesign. This isn't just updating code inside your functions. This is changing the whole architectural design of a system during its software creation process. This can even mean a system that is already out there, that is already under continuous deployment. We're making large-scale, major redesigns to the architecture as part of that cycle. Refactoring is also used as a noun. This is a very American thing to do, turning verbs into nouns, or nouning a verb if you like. When it's used as a noun, a refactoring is a single change made to the internal structure of software to make it easier to understand and cheaper to modify without changing its observable behavior. So the key point of this is that a refactoring does not change the external observable behavior. We're going to maintain the same interface, the same API, and we're only going to refactor the internals of the code. Now, why would we ever want to do this? If the code is already working, by definition, if we're keeping its observable behavior the same, we're not changing anything that anyone outside can see. Is this just a complete waste of time? Is this just about software engineers wanting to make their code look beautiful without actually doing anything useful for their users because they're not changing the observable behavior? So the reasons you might actually want to do this are fundamentally to do with making your code more beautiful, but we do that for a reason. Beautiful code is easier to maintain. It is easier to extend with new features and also with new high-level concepts which give rise to those features. So we've seen the software lifecycle becoming this tighter and tighter iterative process. More and more parts of the traditional waterfall process are getting pulled into this cycle now. And this includes everything. This includes the architectural high-level design of your software. It includes the underlying concepts that your software is for. It includes changing your business case as you go along. All those things are going to change. And so you are expecting your software to have to be modified in all these different directions as these new ideas come in. And in order to make your software modifiable or maintainable, it has to be beautiful. It has to be clean. Everything has to be in a logical place so that you or probably other people can come in and easily find ways for the software to be changeable, extensible. Sometimes you will refactor for performance reasons. We talked in a previous session about profiling. So you can view profiling as a particular special case of refactoring where computational speed, especially real-time performance, is the most important issue. So when you profile, you want to go through the same process. You don't want to change the external behavior, but you want the thing to go faster. Often you will want to do this specifically in response to one of the anti-patterns that we talked about in our design patterns session. If you've picked up on a code smell, that's an indication of one of these standard anti-patterns. That can be a strong hint that you're going to need to do some refactoring to update the design and keep your code clean and maintainable and extendable. A general reason for having nice, clean code at all times is to build your community. As you go through the development cycle, many times you will learn more about what it is you're doing. Very few projects start off with a perfect design. You will always learn more about the underlying concepts of what you're doing by performing experiments in software development. You will try different things. Sometimes they work, sometimes they don't work. You will learn from them. You will update as you go around. And if you If you keep iterating, keep your code clean, that makes this a nice project that other people are much more likely to come in and get involved with. It's a great way of turning your users into developers if they see this is a nice place to be. The obvious danger with doing this, if it isn't controlled, is breaking things. By definition, we have a piece of code that is already working, so this is not about debugging. Refactoring is a distinct process. That's why we have a different lecture from debugging. We want to keep the behavior the same. So we have code that is already working, and there is an obvious risk here that if we go into working code and start changing things, we could be introducing new bugs. So if you only learn one thing about refactoring from this lecture or from this book, it is here in bold, and that is you wrap any unit in tests before you do your refactoring. You're going to define what the behavior of this unit is supposed to be, create the tests for it, and as always, you can then go off and change things, modify things, and you only accept them when they pass the tests. Okay? So before you attempt any refactoring at all, always wrap the thing in tests. It's going to keep you sane through the whole process. Once upon a time, this was a very controversial idea. This is all tied up with the demise of the waterfall Gantt chart approach to doing things. The idea that you could iterate your design as well as your implementation was, at the time, considered crazy. This is all part of the move towards what are often called agile development methods. The idea that you start with working code. The first thing you do, even in your design process, is not get out a pencil and draw a UML diagram, but you write actual working code and you generate your UML diagrams and designs from the working code. You start by hacking something together, you make it work, but then you can progressively add tests, perform refactoring, and make the design more beautiful and more robust as you go along. So it's not so controversial today. That's because of the hard work done by Martin Fowler and all the other people who were involved in pushing this idea. So refactoring today means two slightly separate concepts. There's the general idea of refactoring. That's the general idea that you're going to wrap some code in tests, you're going to maintain its external behavior, and you are going to do stuff inside those units to make it more beautiful. That's the general concept of refactoring. What we have also seen over the last couple of decades has been the development of much more formalized standard approaches called refactoring moves. Refactoring moves are specific defined steps in various types of refactoring. As we saw in design patterns, there are standard things that often come up in many different software systems. In refactoring, there are standard things that you do to make code more beautiful that come up again and again. So when refactoring began, it was a manual process. It involved you writing the test, then you'd go into the code and you'd make these changes using your favorite coding text editor. Some of these moves were picked up by Martin Fowler and others, and Fowler did the excellent work of putting them all together in a big book, and as with design patterns, giving them names. Once you name these concepts, you pin them down and you can start to control them. So these can be changes. For example, renaming a method is a basic refactoring move. You might want to take your whole project and make sure that a method is updated. The name of the method is updated all the way through the project. And there are standard ways that you go about doing that. You need to change the definition of the method, and then you need to go through the rest of the code and look for everywhere that the method is being called. And in the most mechanical way you can, you need to make sure that each of those names are updated as well. This became such a well-defined and mechanized process that many systems have now completely automated it. So instead of performing these standard refactorings manually using your text editor, most languages will now provide tools that will do them for you automatically. This is closely linked to the concept of static analysis. In static analysis, you parse the code, you understand its structure programmatically. But here we are going to go beyond static analysis and actively change the code. So typically this process will start with a static analysis tool, but then there will be additional tools that actually make these changes. So for example, you don't manually rename a method all through your project anymore. You're going to find something probably nowadays in your nowadays it will be mapped to something in your editor. For example, here's I think this is maybe Eclipse or Visual Studio Code. You can see there is a refactoring menu. There is a menu of specific refactoring moves. You can go in there, you can find a move like rename method, and that will ensure that the method is correctly renamed all the way through the project. There are about 100 of these refactoring moves in common parlance. As with design patterns, there's a canon which is debated. Many of them come from Fowler's original book. Some of those have been built into the more popular code editing programs and the software tools underlying them, but there continues to be debate about what are the best moves. I just had a question from Gary. How do you choose what needs refactoring? Is everything up for grabs? Good question. What we're fundamentally trying to do in software architecture is create good code, clean code, good design. It's difficult to define exactly what that means. It's something you gain with experience. It's something that graduate programmers typically don't have. You learn it as you progress in your career, as you become an architect. The basic concept here is to make your code clean and good designed in the sense that whatever you are currently wanting to extend into will be available. You want your code to exist in a state that makes it extensible in the directions that you currently need to go into. So yeah, if you're doing this with the tests, as long as you respect the external interface, everything is up for grabs. As long as you don't change the behavior of the code, you can do whatever you like inside. Okay. So that was the concept of refactoring moves then. This began as a manual process. Martin Fowler's book defined what those manual processes are in a way that a generation of programmers learned to do them manually as these mechanical processes, and now they've been automated and put into all your favorite coding editors. So as with design patterns, we can't look at all of these because there's about 100 of them, but I'm just going to give you a few examples to give a flavor of what else is in Fowler's big book. Here's a very simple refactoring move called add parameter. And in this case, we want to change the interface of a function. This is usually done because we want to add some extra functionality to a method. You may have a method that works, it's already doing something, and now you want it to do a bunch of other things, or you want to make it more general, or you want to allow the user to have more control over how it's doing those things. So we're extending the functionality of a method. So for example, here we have a UML diagram. We begin with a customer class. There's a get contact method that's going to return their telephone number, for example. And here we've now decided we want this to have a new kind of functionality. We want to specify a date. We want to specify the contact method for a customer on a particular date rather than in general. So as with many of the refactorings, you don't just update this in the definition of the function itself, because you have to consider who are the users of this, who's actually calling the method. So as part of this refactoring move, we're going to hopefully automatically now go through the whole code base via static analysis, find all the calls to that function, and update all the calls at the same time as we do this. Sometimes when you do this, you might want to not break existing calls. You might want to leave this function so that if there are users out there, especially external users who aren't part of your own code base, You might want to not break this by making your new parameter into an optional parameter, or a parameter that has a value. That means that you're not breaking the API for your external users. They can continue to call you in this way, even though your function is really doing this. And so to implement this, we'll do static analysis. We have to do a full parse of the code to understand where getContact is actually being used as a method name. It's possible, for example, getContact could be used as a variable name in other places. We don't want to interfere with those uses of the word. So you have to do full parsing and static analysis to find where these cases are. And after the static analysis, we have an update step that actually changes them. Okay, so a similar idea is renaming a method. Here's our UML diagram. Here we've got a abbreviated get in CLT limit, and we've decided as part of our design we want to make all our method names nicer or more standardized, maybe to comply with somebody's coding standards, and we want to use this longer name like get invoiceable credit link. So the mechanics of this are very similar to adding a parameter. We're going to have to find not just the definition but all the uses of that method via static analysis, and then apply changes across the whole project. And again, being very careful, because the same name can appear for different things within different scopes in the project. There might be a variable which has the same name. So we need full parsing, full static analysis to be able to do this properly. Okay, pulling up methods and pushing down methods. This is to do with object-oriented programming, where we have a class hierarchy. As your design progresses, you will learn more about where in the hierarchy your functionality should live. For example, here we have employees, a class of employees. There are subclasses of salesmen and engineers. And perhaps this project has evolved over time. Someone decided that salesmen need a name, so someone added a method getName to salesman. That would be the programmer who is only working with salesmen. Maybe independently, someone was working on modeling engineers, and they also decided to have a getName. And as part of your refactoring audit, you notice this functionality is getting duplicated, and that this function really belongs in the superclass. Having a name and getting the name isn't a property of salesmen or engineers. It's really a property of employees that should be inherited by salesmen and engineers. So this is called pulling the method up into a superclass. Sometimes you want to go the other way and you have push down method. You can take a method from a superclass and put it into one of the inheriting subclasses. So as with the other refactorings, this began as a manual process. Martin Fowler wrote down all the steps for doing it, and then authors of software tools have picked it up and turned it into these fully automated processes. So as always, you have to do this properly with parsing, with static analysis. You need to be very careful around things like user casting. If a user is taking a class and casting it to another class, be careful where these things end up. What would happen, for example, if the superclass already has the method getName, or if it has a different method that has the same name? Are you going to clobber that name? Are you going to raise an exception? Are you going to make sure the user calls a function with a slightly different name? There's a lot of subtlety about not breaking everything else in the code. Another example is replacing data with an object. This is a very common thing to do as your program grows in complexity, and you learn from your coding experiments. You learn that you have to model more things in the world in more detail. So it's very common at the lowest level of your object hierarchy. It's very common to represent some objects in the real world, not by programmatic objects, but just by basic variables such as strings. Now, for example, here we have an order. A customer has placed an order, and the customer is represented just by a string. That's the name of the customer. And this could have been working very well. This could have been in the database for many years. And then one day you now need to do something extra with your customers. You're going to implement a new customer management system where you want to model what is your customer interested in, what have they been buying recently, all this extra stuff that will help you sell more things to them. So now your customer isn't just a string, they're not just a name anymore, they're going to become an object, which could potentially be filled with all this extra information. So at this point, we have a member variable inside that class, and we want to convert that into being a class itself. We want to create a new class called customer, and everywhere we used to talk about customers as strings, we're going to automatically update that with a reference to this new customer class. Again, all of this should be done automatically now. We're going to run static analysis on the system. We're going to automatically create that new class. We're going to automatically go around everyone who was talking about customers as strings and automatically get them updated to using the class. Questioning, how is pulling up and pushing down methods different to upcasting and downcasting? Okay, so upcasting and downcasting is when you take a particular instance of a class, a particular object, and you convert that instance to something higher or lower in the hierarchy. Pushing up and pulling up and pulling down are things you do at the class level. You're moving the method itself from one layer to another. So you could probably get the same functionality by upcasting and downcasting, but it would be messy, and indeed that could be a code smell. If you see yourself doing a lot of that, that's probably an indication that you should be doing this kind of refactoring and putting the method in the right place in the first place. Okay, that was replace data with objects. So now let's take a look at replacing method with an object. Now this one is a little controversial. This is a very Java-ic thing to do. It's a very 1990s object-oriented style, and it's actually the kind of thing that is mocked heavily by people coming from other languages. So the idea here is you begin with a function. For example, here's an order. The order has a function price, which is going to give you the price that is part of the order. And you will sometimes find yourself adding more and more parameters to this function, and it grows and it grows. And in some cases, you will keep calling the function with the same set of parameters. So for example, you might have decided all your orders are getting done in euros, and you set the currency of all these orders to euros. And so now you find that every time you're calling this function, you're giving a huge list of parameters that are always the same. You're always telling it to do it in euros and giving it the same date and the same customer and so on. Now, if you believe in object-oriented programming, you consider this a bad thing because these parameters are hanging around, they're getting passed again and again, and it would be more beautiful from an object-oriented point of view to just set them once and have state inside that method. Again, there are ways of hacking this. You can put a static variable inside your method. If you see yourself doing things like that, that could be an indicator that you should be fixing this and doing it properly. So what object-oriented people would want to do at this point is turn that method into an object which can hold its own state. So instead of just having a method called price, there's now going to be a whole object inside the order called a price calculator. Now notice this is a noun. A price calculator is a thing, whereas a method is usually a verb like get price. So where we had get price, we're now going to have a noun, a price calculator. And by including the object here, you can now set the state. You can tell this thing what the currency is, who the customer is, what the dates are, and then just leave them there so that you don't have to call them with these same parameters again and again. As with all the moves, this used to be a set of manual steps. You have to first change the implementation, look for all the things that are calling it and update those, and is now incorporated into many of these automatic tools. This is controversial because it is considered a bad thing by other programmers. So in particular, functional programmers do not like state. Functional programmers would actually want to do this refactoring the other way. They would see objects like this price calculator and say, this is a horrible Java-ic thing that needs to be removed. So you might see people from a functional background actually run these refactors with their own automated tools that go the other way, that turn the thing back into a method again. Reasons you might want to do that are to do with reducing the state. When we talked about debugging, we saw it's harder to debug things as the state space gets larger, because you have a bigger hypothesis state for isolating where the bug is. If you can remove all that state and go to a more functional style, that's supposed to make the debugging easier. A final example, extract class. This is a very classic concept, well known in database world. This is the object-oriented analog of what is called database normalization in SQL and database theory. This occurs where you've put too much information in a single class that really should be spread out. For example, here's a class of persons, and we've given the person a name, an office area code, an office number, and a method called getTelephoneNumber. Now, the problem here is that we've assumed that one person has one area code and one number, and that those things are properties of the person, when in fact, the area code and the number are really properties of the phone number itself, or possibly of a physical phone. So another way to do this would be to create a phone object or a telephone number object. So for example, you might nowadays have people who have multiple telephone numbers. A person might have a mobile phone and an office phone and a home number. Maybe even they have several mobile phones. And you can't represent that if each person only has a single variable for number and area code. So when that happens, you need to separate the representation. You need to have the class of persons and a separate class of telephone numbers. So the area code and the number are now properties of the phone number rather than properties of the person. And the person has a telephone number, or now they could have several telephone numbers. As always, there were manual steps for doing this. You could go in, identify these things, go through Martin Fowler's manual step-by-step refactoring program in your own editor. As always, those things are now put into automated tools. So you wouldn't do this manually anymore. You would run your refactoring tool and say, please extract these members, area code and numbers, please extract them into a new class called telephone number, and all the other changes to the structure will be done automatically for you. So these were just a few examples of relatively small scale refactorings. It tends to be the smaller ones that are the most used. There are also proposals for very large scale refactoring moves. For example, in the design patterns lecture, we talked about the factory design pattern. Sometimes you want a separate structure called a factory, which creates objects independently of their constructors. So for example, you can configure your factory to produce widgets for different graphics system backends. So you'll see, for example, proposals for refactoring moves that will automatically convert a object constructor into a factory. You'll find a refactoring move built into some tools called convert constructor to factory. That's doing pretty major surgery on your code automatically. That's creating a whole extra layer, an extra factory structure, calling out to different constructors, doing a lot of work for you. But again, ideally all automated nowadays. Those are examples of refactoring moves. Then the moves can be done manually. They were originally done manually. What we've seen now are tools which try to automate collections of these standard moves. Some of the moves don't require fancy tools. Some you can just do yourself using automated commands. For example, if you know your program has a lion class and you want to turn it into a tiger class, and if you're sure that you're not reusing those variable names anywhere, so you don't have to deal with scoping rules and static analysis, you could just give a command like this. This is just going to substitute lion and tiger in your code, in all of your Python scripts in a directory. That's just a one-liner at the command line. But this isn't going to scale. As soon as your programs get more complex, or as you want to do more complex refactoring moves, you're going to need proper tools for doing that. In particular, you're first going to need a static analysis tool to parse your code, and then you're going to need a tool which takes that parsing as its input and takes some instructions from you as a user and performs the actual refactoring to perform changes on the code. This is going beyond static analysis. We're not just analyzing the code, we're going out and changing it now. We can do this at the code level. You wouldn't often do this in high-end professional coding, but it's worth looking at for educational purposes at least. Here's the actual API to a refactoring system. So Rope is a refactoring tool for Python. These tools are obviously very language dependent. What it means to do refactoring can be completely different in different languages. You'll have different moves, different static analysis. So you'll see completely different tools for each language. They might have moves with the same names, but they're going to get implemented in different ways depending on the concepts that are built into the language. So this is just an example for Python. We can install Rope like this. We have a concept of a project. So when you work just with compilers, a compiler takes a single source file as its input and it compiles it. When we get to projects, a project is a collection of files that are intended to be compiled together. We've seen this concept come up when we talked about build systems. This is the same idea showing up in a refactoring tool. So we have to have the concept of a project. Here we're making a project object, and the project keeps track of which files go together to be compiled and refactored together. So here we can represent a file from the project. Here we're doing get file. And in this particular case, we're going to rename the file. We're going to rename the source file. So this means not only changing the file name on the system, not just the name of that particular file, but everywhere that that file is used, everywhere that someone is importing that file, that has to be updated automatically as well. So here we're importing a rename functionality from the refactoring tool. And you will usually see, for most tools, these two stages. First of all, you get the changes. So we're doing a rename. We're saying we want to rename this file to a new file name. This is going to return a set of recommended changes as a programmatic object. So at that point, we might want to look through the changes, inspect them, make sure everything looks okay. And then we actually apply the changes, in this case with a do command. That's actually going to go out and edit our source code for us to make all the desired changes. Here's a couple more examples. Here we're renaming a variable throughout the whole project. Again, being very careful with scoping. There could be multiple things that all have the same name. We only want to rename them in the correct context and scope that is intended. So again, we will import a name functionality. We'll tell it in the case of Rope, we tell it where in the code is the current name. We can't just say rename cat as dog, because the word cat could be used in multiple locations to mean completely different things. So we have to say which instance of cat is getting renamed. We do that by saying which file is it in and which character in the file. This is character number 12 in that file is the particular instance of cat, and we want all the other cats that refer to the same entity as this cat to change. But if there are other things called cat that are different objects, we don't want to touch those at all. We want to leave those alone. So here's the rename. That's going to give us some changes. We can check them if we like, or we can apply them by running do on the changes. Or similarly, if we want to rename a method, similar process. Again, we have to specify the file and the character locations in the file so that we know which version of that method name is being used. You can't just give the method name because there could be multiple things having the same name for different things in the project. These are all quite simple refactorings. As I mentioned, there are much larger, much more complex refactorings. If you were, for example, going to introduce a factory class automatically, convert constructor to factory, you could have a similar interface in your refactoring tool to this, but it's going to go off and do much more complicated work under the hood. If you want to play around with rope, here's the URL for it. Rope is a nice example of a documentation concept I've talked about before, which is using unit tests as the documentation. Many people come to rope and they say, where's the tutorial? Where's the docs? I don't know how anything works. And the answer is it's all in the unit tests. The unit tests for this are lovely. They're written as a end user tutorial. So you can manually step through the unit tests, try running each one, and that will teach you how the whole system works inside. So if you like to do your refactorings from a programmatic API, that's one option. It's more normal to integrate tools like that into our editors so that we have some kind of interactive experience as a programmer. So for example, here's how I do this in my Vim setup. You can see this is an interactive session using rope. So remember, you have to specify which instance of a name is being used. So if you're in a text editor, this is a nice way of doing it. You can move your cursor to a particular line, a particular instance of the word cat, and then hit the command for rename variable, for example. And then most refactorings will then require some more information from you to figure out exactly what it is you want. So you see this has started an interactive session. It's a question and answer session. So rope is asking me, do you really want to rename this thing? Yes. What do you want to rename it to? If there are any conflicts, so if I already have something called dog, for example, do you still want to rename this as dog, or do you want to think again, or do you want to rename the other dog as dog 1 and dog 2 or something? So some of these will lead to quite long interactive sessions as the refactoring system figures out exactly what is wanted. If you want to run this on your own machine, again, rope is for Python. I'm running it in Vim. So there is another tool called rope Vim that will take your Python rope refactoring library and it will give it this binding into Vim. And then you can map the keys. So for example, if you do external command, then R for rope and R for rename, again, this is talking VI language. You're giving a sequence of keystrokes to say what you want to do. I want to give an external command. I want it to be a rope command, and I want to do some renaming, please. That will take me straight into the refactoring. Other systems will have graphical interfaces. You might see this in Eclipse or in Visual Studio. They're just getting the same information in a graphical format. You can see lots of things to click on, lots of options, lots of text boxes to fill in all that information. Rope Vim is especially nice to use and to install because the documentation for it was written by me. I just had my pull request accepted, which is a great feeling. You can contribute to all these projects, not just by writing code, but by contributing documentation. It's often the case that the people who write the system are so in the mindset of the system that it's hard for them to explain to an outsider how the thing actually works if they're just starting out. So I went through that process as a beginner and I figured it out, and I made the documentation a little easier to use. So this should now be very easy for you to set up in your Vim at home if that's your thing. So we've looked at we've looked at refactoring tools. Let's also talk about when this should be done. So Gary was asking what is actually on the table for doing this. The aim of this is to create this somewhat mythical and subjective concept called clean code or good design. And people will argue over what this means. I think most people recognize clean code and good design when they see it, but they find it quite hard to explain exactly what it is. Many people say it takes decades of experience to pick up. But roughly, it is referring to this ability to extend the code. At any point in the life of a piece of code, there are certain things that you want to do with it. There are certain extensions, new features that you want to be adding. And your code is well designed or is clean code if it's easy for you to do that. If everything is in a state that just lets you bolt on your new thing, then that will be a nice experience. The code is clean, it's well designed. Um, not having bugs is always nice. Actually, not so relevant for this particular topic. We talked about debugging in a separate session, but the simplicity of debugging is part of clean code and good design. Is the code set up in such a way that enables you to easily get in there with a debugger? Does it have the correct kind of state space? Has the state space been minimized to enable nice debugging? Is it easy to test the code? Is it easy to add new unit tests? Is it easy to see what the current tests are doing? Is it easy to fix the code if any of those tests fail? And is it easy for new community members to come in and understand and join in the project? There are examples, especially from the original GNU systems. So systems like the GCC compiler has been hacked together piece by piece for many decades, and it works really well, but it's getting harder and harder for new people to join the community because of its structure. So in the case of GCC, we started to see that being challenged now by other compilers, like the Clang compiler some of you guys are using, which has specifically been designed up front with a nicer design. Probably based on a bunch of stuff that has been learned from the experiments done on GCC development. When we talk about the ease of adding new features, it's important to realize that this criterion changes over time. You don't know now what are the new features that people will want to add in another 10 years. So you can make what you think is the best design in the world now, but in 10 years' time, if everyone decides then that a customer isn't just a name, but a customer is actually this complex human being with desires and history and interests and all this stuff that can be used to manipulate them and sell them more stuff with customer management tools, then all of that design is going to have to change and be extended with those new concepts of what a customer is. So when we talk about clean code and good design, it's subjective in the sense that it depends on what are your currently desired new features. If you are desiring to extend your model of a customer with all that extra richness, then a good design or clean code now is any class system that will enable you to do that particular extension very easily. But for someone else who comes in, maybe at a different time, if they actually want to make the system all about orders and accountancy and implement the new tax regulations that come in the year 2038, then they will care more about the clarity of the models of the orders and the interactions between customers and sellers. So this is always a shifting target. I think clean code and good design is relative to what you currently want to do. Even if you have ideas about what might happen in the future, we might guess that one day people want to improve the customers or the orders. That's still subjective as well. That's still just based on your best guess of how the system might evolve over time. And that guess itself is also going to evolve over time.
Did you use 2038 on purpose?
That's an interesting year, yeah. So the opposite of clean code is what is known as technical debt. Technical debt is the name for the accumulated lack of refactoring. If you have a system like GCC, for example, it's grown over time by people bolting more and more bits onto it, but without any large-scale design refactoring. You will see that this creates a ticking time bomb for the future. It can be kept hidden for years or even decades. The code is still working. Remember, refactoring is always about keeping the behavior the same on the outside. But technical debt will accumulate. The code is getting more and more messy. It's getting harder for anyone to add new features. It's getting harder for people to debug and fix. It's getting harder for new people to join the project. And this is a major cause, possibly the major cause of failure for both projects and entire companies if technical debt isn't being controlled correctly. It's a very difficult thing to control because it is so hard to measure. It's because the external behavior of the system stays the same. So some managers will actively discourage you from doing refactoring because it doesn't appear to be creating any value. You're just working on the inside of the system without adding these new features. This could be a fun way to make money, right? If you can find who these companies are, who's got this hidden pileup of technical debt inside, you could get in there and short sell these companies. That's where you sell shares that you don't have and you're going to buy them back again later. It's like buying a negative amount of stock in a company. This would be a nice little trading strategy if you can somehow get out there, get the rumors, find out what's going on, who's accumulating technical debt. For example, if you were let's say a large American operating system, proprietary operating system company, and you've spent the last 20 years just bolting on hacks and kludges and trying to keep everything back compatible, you might believe that one day in the future, all of this is just going to fall down in a mess of technical debt. So you could go in there and start short selling that company to make a nice profit sometime in the future. So Martin Fowler talks a lot about this issue of when to refactor. In some projects, it's planned into the project as a scheduled or workloaded activity. So even using a waterfall model, you could include this as a box on your Gantt chart. You could say, we're going to do our whole project. I don't know if any of you have already thought of this in your student projects. You could do your whole project, you could write the documentation, do your demo, and then have a refactoring stage at the end where you say, we're going to spend 3 weeks looking at what we learned. We had this initial design idea. Some of it worked, some of it didn't. The stuff that didn't, we're actually going to go and fix it. And we're going to allocate in advance 3 weeks for doing that. So in other cases, you won't plan it in advance, but you might plan it dynamically. You might notice things are starting to get messy. You notice that technical debt is starting to accumulate. And at that point, someone says, hey guys, should we now allocate 3 weeks for sorting this out? We're not going to add any new features. The external behavior is going to be the same, but we're going to get rid of that technical debt. We're going to get the program nice and clean so that it can be extended in all these different ways in the future. So these are still quite waterfally, old-fashioned approaches to it all. What we see now, as always, is the iterative cycle getting tighter and tighter. We'd really rather do this as part of our everyday work. Every time you make a change to the system, you can consider refactoring in the back of your mind. Is there something I can do even when I'm just reading the code? Many of us enjoy reading source code. We just download open source projects and we look at them to learn different styles of coding. But even as you read something, can you just go in there and make a few little changes, as you do on Wikipedia, just to tidy things up? Leave the behavior the same. Make sure you pass the tests, but just make things a little tidier as you go. Some people like to do this before a major change. Some people will do it after a major change. One philosophy is to do it when you are about to make a major change and you notice the technical debt has accumulated. Especially if you have an uncooperative manager, you can convince them that it's worth doing the refactoring now because it will reduce the amount of effort that is needed to do that change. If you go in and make the change in a hacky way, it's going to take 3 months. But if you spend 3 weeks refactoring, then you can make the change in just a few days because you have nice clean code. Or other people might like to do this after they've made a change. As we said, every time you write code, you learn something, you've found out something new about the design, it's going to become part of that iterative cycle. What have you learned from doing it? What does that enable you to tidy up after you've done the work that you didn't even know about before? So there's often this problem with unenlightened management. If your manager doesn't understand this and they're pushing you to make more money and add new features, there is always this danger that poor management will just accumulate technical debt, and eventually the thing will get so big that the whole company comes crashing down. If you have a more enlightened manager, they will understand that it is worth doing this. It can be a hard sell though, right? That you've been asked to add a new feature to the code, you're given 3 days, and that's going to work you pretty hard. And now you want to argue that you're going to spend the whole one of those days just improving the design of something that already works. You're not going to add any extra new features, any new functionality, pass any new test. So Martin Fowler is also a kind of sociologist of Silicon Valley working practices. He's famous for recommending that you should do this anyway, even if your manager doesn't like it. As a software creator, you have an obligation, whether you consider yourself a member of a profession or a community, or whether you just consider you personally have a reputation to maintain. It's an essential part of the software creation process that code is kept in a clean state. And so you have to do this refactoring. Even if you've been told not to, you should go and do it anyway, because one day these people will come and thank you when their company doesn't actually fall over in 2 years' time. Okay, so that's refactoring. Refactoring is a verb to be doing refactoring. It is also used more specifically as a noun, specifically for one of these formalized automated refactorings. Extract method is a formalized refactoring that is built into many of these systems. We want to do this to make our code clean, specifically to prepare for the addition of new concepts and features. It's about making your software maintainable and extensible. And we don't know what those directions are going to be at the beginning of a project. The design and these extensibility vectors have to evolve as part of the development cycle, along with everything else. Sometimes we'll do it for performance, especially for speed. That's known as profiling. Often we'll do it in response to these code smells and anti-patterns. Again, if you read Martin Fowler's books, there are specific treatments for anti-patterns. And many of the refactorings are directly linked to those. You'll say, if you see this code smell, that means you have this anti-pattern. The treatment is you do this, this, and this refactoring, and that will bring you into a nice design pattern, a well-known design pattern, the way things should be. And you keep your code clean to make it a nice place for new community members to come in. So, for example, if you want to join the compiler community, maybe you're more likely to go and join Clang today than you are GCC, because Clang has the nicer design structures for you to get involved in. How do you do this? The golden rule is you don't break anything, and you do that by wrapping everything in unit tests before you do the refactoring. As long as you continue to pass the tests, you can do whatever you like inside, including both standard refactoring moves and customized manual refactoring. So at least in theory, we have these nice automated tools today, which means they will always work. When this began, the tests were really important because it was a very error-prone process to do these steps manually, and you needed the tests to make sure it was still working. Ideally now, you're just going to click on rename method, and that's guaranteed to work across the project. Still good to wrap in tests anyway, A, because those tools might not always work, or B, because you might want to do more informal refactoring along with the formalized moves, and when you're doing manual coding, you always risk breaking things. And we talked about when to do this. The best way to do it is continually as part of this iterative process. Every time you even look at code, this should be like a quantum thing. Every time you read someone else's source code, just go in and make it better as part of the reading process. Every time you're asked to add a new feature, don't just add the new feature, but do a little bit of refactoring and keep the code tidy as you go along. And remember, it's always a moving target, because what is meant by clean code is the ability to extend in currently interesting directions. Those directions will always change over time. Okay, happy refactoring.